In this video, we will learn how to simplify square roots. So what we're going to do today is we're going to look at what happens or what we do when the number underneath this square root isn't a number that can be perfectly square rooted. So if it's something like a square root of 100, we know the square root of 100 is 10. Or the square root of 36. The square root of 36 is 6. Those are really nice numbers that can be perfectly square rooted. Unfortunately, though, 90 is not one of those numbers. And if we take the square root of 90, we end up with this crazy number of 9.48683298, and then that number keeps going on and on and on and on and on forever. The square root of 90 is actually an irrational number that continues on with numbers for all of eternity. So this number isn't something we can easily come up with. We need our calculator to help us out. But unfortunately, if we round any of these numbers, so for example, if we write 9.49, because the 6 rounded the 8 up to 9, technically this is called an approximation because it's not exact. There was some rounding involved, and as a result, it went from being an actual number to an approximation. So what we're going to learn today is how do we simplify square roots so that it looks a little simpler, but also is still the actual representation, not an approximation. So that's what this video is going to explore. Now, the definition of a simplified square root is a square root where the number underneath the square root will have no perfect square factors. So what this means is that the number underneath the square root is not divisible by any perfect squares. That's what that word factors really is telling us. Now, what gets confusing here is if you don't know what a perfect square is, it's really hard to tell if our number underneath the square root is divisible by any perfect squares. And perfect squares are numbers that can be perfectly square rooted. So unlike the square root of 90, these numbers, when they're square rooted, produce an integer. And the way to calculate these is to think of numbers squared. So I know that 1 squared is 1, so I know that 1 is a perfect square because I can square root 1 and it will equal 1. Then if I think of 2 squared, that is 4. So 4 is another perfect square because 2 times 2, or 2 squared, gives me 4. Then my next one is 9 because of 3 times 3, 16, 25, 36, 49, 81, 100, 121, 144, and so on and so forth. So all of these numbers can be perfectly square rooted, and you can easily come up with a list of these by simply going 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc., etc. So what's going to happen is if we have a perfectly, I forgot 64 in there, so there's my 8 times 8, 9 times 9, 10 times 10, 11 times 11, 12 times 12. And these are really the only ones that you need to know. But what's going to happen with us when we simplify square roots is we're going to be checking to see, is our number divisible by any of these values down here? And if it is, we're going to do our best to rewrite it so that we ultimately end up with a number underneath the square root that is not divisible by any perfect squares. Now, the best way to learn how to simplify square roots is to actually just jump in and do a couple of examples. So the first thing we're going to do here is we're going to check and see if 200 is fully simplified or can be simplified further. And remember, if a square root is fully simplified, the number underneath the square root will not be divisible by any perfect squares. So I'm just going to go ahead and list out my perfect squares. So I have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and so on. So if I look here, what I notice is that 200 is divisible by quite a few of these numbers. So all I have to do is start doing 200 divided by any of these. Now, every number is divisible by 1, so you can kind of ignore the 1. But if 200 is divisible by any other of these numbers, then it is not fully simplified. So if I divide 200 by 4, I find that 200 is evenly divisible by 4. 200 divided by 4 is evenly 50. So it's divisible by 4. If I keep going and testing, it's not divisible by 9, not divisible by 16. It is divisible by 25, as 25 times 8. Not 36 or 49 or 64 or 81. It is divisible by 100, because it's divisible by 100. And then 100, if we were to take 200 and divide it by 100, we would get 2. And then here we have 121, 144 that aren't divisible. So what I notice here is that 200 is divisible by 3 perfect squares. And as a result, it is not a simplified square root. So what we're going to do in step 1 is we're going to rewrite this number under the square root as a multiplication problem using one of its perfect squares. And I'm just going to pick one of these, and I'm going to pick 8 and 25. Doesn't matter which one you pick, that's just the one I'm going to pick. So now if we take the square root of 200 and rewrite it, we can rewrite it as the square root of 8 times 25. We can do that because 8 times 25 is 200. And then using the product property of square roots, I can actually split this up into 2 separate roots. So it's basically using that product property backwards. Now from here, the second step says evaluate all perfect squares and multiply them together. Well, I notice that 8 is not a perfect square, but 25 is, and the square root of 25 is 5. So I really have 5 here times the square root of 8, which the order there bothers me a little, so I'm going to rewrite this as 5 times the square root of 8. So that's what I have so far, and it looks a little bit simpler, but in step 3, we need to keep repeating this process until the number underneath the square root isn't divisible by a perfect square. So that means I need to check 8 and make sure that 8 is a fully simplified number underneath that square root. Well, if I go in, what I notice immediately is that 8 is divisible by 4 and can be written as 4 times 2. So then what I have to do, because I find out that 8 is divisible by a perfect square, is I need to keep going. So I'm going to write this as 5 times the square root of, this is 8, which now we're going to rewrite it as 4 times 2. And then from here we're going to split it using that product property. So we have 5 times the square root of 4 times the square root of 2. And then I notice that the square root of 4 is 2. So I'm going to rewrite that there as 5 times 2 times the square root of 2. Then I notice I have 2 numbers outside of parentheses being multiplied. So those evaluate to be 10 times the square root of 2. And then I repeat step 3 here, and I look at 2 and I say, is 2 divisible by any perfect squares other than 1? And I notice that the only perfect square less than 2 is 1. And that one's not counted because every number is divisible by 1. So what I'm noting here is that this is finally fully simplified. And we have 10 times the square root of 2. So let's practice a few more together. The first thing I need to do is I need to write down all of my perfect squares so I remember what I need to look for and make sure that my number under my root isn't divisible by. So I have 1, 4, 9, 16, 25, 36, 64, 81, 100, 121, and 144. And I forgot my 49 in there, so there we go. Now we have all of them. So what I'm going to do next is I'm actually going to start looking at each number and seeing if I can figure out what that number is divisible by. So if I start going through 117, what I notice is that 117, if I look at all of these perfect squares, it's divisible by 9. 9 times 13 gives me 117. So since 117 is divisible by a perfect square, it's not fully simplified. And as a result, I'm going to rewrite this as the square root of 9 times 13. So notice I took 117 and rewrote it as a multiplication problem. Then, due to the product property of radicals, I can split this into the square root of 9 times the square root of 13. Well, I know that the square root of 9 is 3, so I'm going to rewrite that as just 3. And then the square root of 13 is by itself. Then if I look at the remaining perfect squares and I go through, I notice that 13 is not divisible by any perfect squares, and as a result, the square root of 117 simplified is 3 square roots of 13. Then if I move on and look at 192, if I start going through this list, I'm going to find a variety of things. 192 is divisible by 4. 192 is divisible by 16. So we have 4 times 48, 16 times 12. I also find that 192 is divisible by 64. So 192 divided by 64 is actually 3. So here I'm noticing I have 3 different options for how to rewrite 192. And I'm going to take advantage of that larger number with 64. So here I'm going to write the square root of, it will be 64 times 3, because that equals 192. Then from here I have the square root of 64 times the square root of 3 due to the product property of radicals. And then I realize that the square root of 64 is 8. So I'm going to take the square root of 64, rewrite it as 8. So I have 8 times the square root of 3 as my simplified square root. Third example here, we're now going to simplify the square root of 162. And as I go through, I learn that the square root of 162 is divisible by 9, as 9 times 18. It's also divisible by 81, which is 81 times 2. So I'm going to rewrite 162 as the square root of 2 times 81. I can then use the product property of radicals, so I have the square root of 2 times the square root of 81. I then know that the square root of 81 is 9. So this becomes 9 times the square root of 2, which I can then rewrite as 9 first times the square root of 2, and there I have my simplified square root. And then finally, if I look at 432, what I learn is that 432 is divisible by 4. It's really 4 times 108. It's divisible by 16, so it's 16 times 27. It's divisible by 36, which is 36 times 12. And it's also divisible by 144, which is 144 times 3. So with this one, I'm going to take the 12 times 36. So here I have the square root of 12 times 36. Then from here I rewrite this as the square root of 12 times the square root of 36. I then know that the square root of 36 is 6, so this can be rewritten as 6 times the square root of 12, or just 6 square roots of 12. Then I have to check my square root, and what I notice is that my square root of 12 here is still divisible by that perfect square of 4. So here I can simplify this further, so this becomes 6 times the square root of 4 times 3, which is really 6 times the square root of 4 times the square root of 3. Well, I then know that the square root of 4 can be rewritten as 2, so this becomes 6 times 2 times the square root of 3, which then becomes 12 times the square root of 3. And then I note that 3 is not divisible by any perfect squares, and as a result, that is my simplified square root. So now that we've mastered simplifying regular square roots, we're going to look at what we do when we have variables involved. Now, what's really cool about these is that the number part is actually exactly the same. So we still pay attention to our perfect squares, and we are going to look at 48 and we're going to think, okay, what perfect squares is 48 divisible by? And if I look at the perfect squares on the screen, what I notice is that 48 is divisible by both 4, because that's 12 times 4, and 16, because it's 16 times 3. So I know that I can rewrite it as any of those. Now with the variables part, what we need to think about is what a square root actually means. And if you realistically think about it, if I were to take the square root of x squared, we know that the square root is trying to find what when squared gives you the number underneath the square root. We also know that the square root undoes the squared function and vice versa. So the square root of x squared is really x. So essentially with the variables, if we can break them up into little squared pairs, we can then evaluate them down the road using the definition of a square root. So what we're going to do here is we're going to break these variables up into as many squareds as we can. So if we start rewriting this square root, I'm going to rewrite 48 as this 3 times 16. So I have my 16 times 3. I then have an x squared. I then have a y to the 5th, which I know I can rewrite as y squared times y squared times y. So notice I'm breaking them up into little variables squared. And then I have z to the 6th, which becomes z squared times z squared times z squared, using my knowledge of exponent properties. So then from here I can use the product property of radicals. So I have the square root of 16 times the square root of 3 times the square root of x squared times the square root of y squared times the square root of y squared times the square root of y. And then I keep going with all of those z squareds. Notice that everything gets its own little square root. And then from here I go through and I identify all of my perfect squares that I can easily evaluate. Well, here I have the square root of 16, which is 4. The square root of 3 is not a perfect square, so I skip it. Square root of x squared is x. Square root of y squared is y. Square root of y squared is y. Square root of y I leave because it doesn't have the squared piece. Square root of z squared is z. Square root of z squared is z. And square root of z squared is z. So all of these items are being multiplied together. And they all, because they are perfect squares, can be evaluated and taken out of the square root. So now if we combine all of these together, we have 4 as our number piece. So we've used that up. We then have x. We then have y times y, which is y squared. We then have z times z times z, which is z cubed. And then from here I have 2 items that are left underneath the root. Those I simply combine together to be the square root of 3y. So notice we've taken everything out of the root that we can, and then anything that's left is the fully simplified version of what's left underneath the square root that we cannot evaluate further. So let's look through a couple of examples here together. So here in this first one we have the square root of 63 x cubed y to the 6th. So we start looking at the number part first, and we notice that 63 is divisible by 9. It's really 9 times 7. So here what we can do is we can say, well, we can rewrite the number portion as 9 times 7. And then from here we can break up x cubed into x squared times x. So we have times x squared times x. And then we can break up y to the 6th into y squared times y squared times y squared. So we have y squared times y squared times y squared. And then we can break these all up into their own mini square roots. So we have the square root of 9 times the square root of 7 times the square root of x squared with x, y squared, and y squared. And then from here we can go through and we can evaluate the ones that are perfect squares. So the square root of 9 is 3. The square root of x squared is x. Then we have a y, y. So all of those numbers are now out of the square root because we could evaluate those perfect squares. So we end up with 3xy to the third, and then the numbers left underneath the square roots, which are the square root of 7 and the square root of x, we can put together back underneath as the square root of 7x. Then if we look at our second example here, what I notice as I start going through all of those perfect squares is that the only one it's divisible by is 4. And that's because 26 times 4 gives you 104. So then from here I work towards breaking it up. So I have 26 times 4. I then can break up my x to the fourth as x squared and x squared. So I have x squared times x squared, and then I have just times y. So now everything gets its own mini square root. So I have the square root of 26, square root of 4, square root of x squared, square root of x squared, square root of y. Then I go through and I identify my perfect squares. So I have the square root of 4 is 2, square root of x squared is x, and same for the second one. So now if I combine those together, I end up with 2x squared, and then still underneath the root, I have the square root of 26y. And last one, first thing I notice with the number is that the number is a perfect square. 144, the square root of 144 is equal to 12. So that one I'm going to just leave as is. I'm not going to mess with it at all. So we have the square root of 144. Then we need to break up our variables. So we have x squared, x, that gets us 5x's. Y squared gives us our 2. And then w squared gives us our 4. So then from here we can transform this into many square roots. So we have the square root of 144, x squared, x, y squared, w squared. Then we identify perfect squares. So 144, square root of 144 is 12. Here we get x. Here we get x, y, w, and w. So now we can take all of those numbers outside of the square root now and combine them together to be 12x squared y w squared. And then from here the only thing left underneath the square root is the x.